Bismillahirrahmanirrahim. This is uh, this is supposed to be part 4, but it is part 5. Part 4 being very small file, which I mistakenly pressed the save button at an inappropriate time in part 3, and I had to make a small video for part 4. So this is part 5. I'm going to cover LINPACK in this, how to download, install, and configure, do your benchmarking. For LINPACK to work, you need special library, go to BLAST directory, go to BLAST library. This library is available at, let me show you, Texas, not Texas, University of Texas.edu, resources, software, so and so. You can see this, go to BLAST, you click here and it will take you to a page where you can register yourself and download it. So it needs trivial registration. Just a simple email, name, etc. Do that and get the software. I've already downloaded the software for you. It's here in I think it's in this directory. It's in root directory. So let's copy that. Let's on the master node. It's not there. Okay, let me copy this from cp, go to this place, go to BLAST directory. Okay, now it's here. I need to copy it to /cluster/mpi users home directory. Copy, go to BLAST file in this directory, and I need to change ownership. Do I need to? No, I don't need to. su-mpi user, and see the file here. I just untar it. It will create a directory here. Let's go to BLAST directory. Here it's created. So now go to this directory. This is basic linear algebra, some library. Okay, it has a file named makefile.rule. Let me show it to you. It has this on line 16, as you can see here. This Fortran compiler is G77. Some of the documentations or guides will tell you to uncomment this, but I'll tell you not to, because I'm exiting without, or let's undo, exit without changes. Reason is simple. The documentation, official documentation, tells us that it will use G77 if it does not find Fortran 77. So if G77 is going to be used anyway, don't waste time going into this file and editing it. What you want to do now is you are going to compile it. You're going to do quick build dot 32-bit, because this is an i386 machine I'm working on. So do a quick build and press enter. It will take some time. Okay, it's compiled now. Not compiled, it's built basically. Now compile step needs to be done, which is make. Again, that will take some time, so I'll just pause video here. Okay, this is also done. Now you would need to download the high performance LINPACK, and the website for that is this one, netlib.org/benchmark/HPL. Once you go down on this page, you will see two versions, HPL2 and HPL1. So I've downloaded both of them for you. They are in my directory on my host machine, so I'll just copy them from there. scp root at 10.0.0.2:/root/HPL asterisk to this place, red hat. Okay, so I have these two files here now in the home directory of this user. I can extract, let's do version 1, tar xzf hpl.t.tgz ls cdhpl. Okay, great. Now what I need to do is I need to copy a make file from a special setup directory. Copy setup slash make dot linux p2 f blast underscore gm. This is what I'm going to use, so I'll just copy it to my current location. Okay, and I'm going to edit this file. Before editing, I need to make sure where my GCC, what version of my GCC is, 4.1.2, and where my GCC files reside. ls/user/lib/ is it lib GCC /i386 Red Hat Linux 4.1.2 is my version. As you can see here, GCC version this. So list of this. Okay, the files exist, so it's good to go. I need to edit this file which I just copied here. I'll just show you where my current location is. It's /cluster mpi user HPL, and I'll just edit make file make dot linux dot p2 fblast gm. Okay, it needs a lot of editing. CD path is okay. Architecture is this one. Top directory is inside home directories, user home directory /hpl, that's correct. Include bin lib is fine. HPL lib is also fine. I need to edit this file make.linux. I've already checked my version of GCC by gcc-v, which tells me that I am running version 4.1.2. I checked this directory, it shows me that these files are present. Great, so I now go ahead and edit this file, make this file, edit make.linux file, and I need to change certain things in this, so I just move down from the top. Architecture is okay, top directory is okay, mp directory is supposed to be empty, LA directory is not supposed to be like this. I have a file here which I take help from, so I'll just use that to see what this should be. So LA directory should be this one. Copy this and change this to this. LL library also needs to be different, so LL library, I copy this from here and I remove this line and I type this. Okay, good. Now I go down and check for various other flags. CC, let's go to CC. Okay, CC seems to be okay. CC and OOPT is okay. CC flags seems to be different, so this needs to be set up for CC flags. Copy and change CC flags to this one. I think linker is MPICC, yes, MPICC, and CC flags, archiver is okay. That's all. So let's save this file and Next step would be to build this using this command. Oops, I had to show you. Let's Control C, or let me just show you here. I just copied this command and pasted there. Here, have a look at this. Make architecture is equal to this one. So it's completed now. So I'll just check my file. What I have to do next, I have to go into this directory and start doing the actual magic. Okay, so I go into this directory /cluster mpi user HPL bin linux this, enter list, and I've got this XHPL program and HPL.dat. This is one big mess to handle, so let's copy HPL.dat to HPL.dat.original. Now we are ready to rock and roll soon. Now HPL.dat, edit this. This is the LINPACK configuration file. How many processes will be run, what is going to be the number of problems, what is going to be size of problems, what is going to be block size, what is going to be the value of P and Q and the grade and all that. It's quite complicated. So I'm going to tell you a formula to find the value of problem size. Value of problem size can be found first by calculating what is your free minus b tells you. This is your free minus b. Okay, so you go to a node, go BC, it's your calculator, go square root of 0.1 into this value into number of nodes which are going to take part in the calculation. So I'm going to use 2. So I'll just say 2. So it says 5099 something. I can safely assume it to be 6000. Okay, so I'll just keep it like that, and I will edit this file again, and I will specify, instead of 4 number of problems, I'm going to have one problem of size 6000. Okay, that's going to be the size of my problem, and number of blocks I'm going to use is one block. I'm going to use a size of 100, should be a safe size for the block. So one block of size 100. I'm going to use one process grid, and I'm going to use one processor on each node, and there are going to be two nodes. So this is what my calculation is. So P into Q, this is P into Q, but P into Q as seen here is not 2, okay, because I've got only 2 nodes. So P here is basically row and this is column, and these two values should ideally result into some binary number like 2 into 1, 2 into 2, 2 into 4, 4 into 4, 4 into 8, something like that. So should be ideally like that. That should be your number of nodes in total. I save and exit this file, and I execute this program now, XHPL. Before that I have to boot 2 nodes. I should not forget that, and I have to run mpi execute this program. So let's copy this and do an mpi boot. First mpd all exit, no programs running. So let's do mpd boot minus n2. I'll n2 mpd boot. It cannot read mpd.host file. Okay, let's go to this directory, home directory, do mpd boot again. Fine, it's booted. So now I go to my previous directory, and which is this one. I have this file here, and I will just use mpi execute -2 number of nodes, and I'll execute this HPL XHPL program. Now see, this is the real magic. Now this is your benchmarking being done. This will take some time. It will run about 18 tests, and this is the configuration it is going to use. All these values are specified here. The smaller the problem, the less number of time our test takes, but also the less time it gets to do computations. I've already got the first computation test result here. I've got about 6.1 gigaflops. The +00 indicates that this value is just to be read just like that. This is scientific notation. This is number of power, 10 raised to the power 0 basically. So if it is 03, that means you are entering into teraflops, and as the number here increases, you are entering into higher values. So right now I'm getting 6.1, 6.2 gigaflops, and the size of the problem is about 6000, and each time solving a problem is taking about 23-24 seconds. That's good. Alhamdulillah, you can see 6 gigaflops. Okay. After this test is run, this is now done. That means this is your benchmarking. This is how you do benchmarking. You note down this, you save this all into a file. I'll just show you how to do that. Let it finish the test and I'll show you. I'll just pause the video here to save time. By the way, I should tell you that the block size which you mentioned in the HPL.dat size and the number of problem size, the size of the problem should be a multiple of the block size. It means this should be a multiple of this, so it's clearly a multiple of this. That's why I selected 6000. I did not select the actual value which was calculated. Now I can try increasing this value as well in future tests. I'll show you. It will take more time on each problem, but let's see if it can do more processing. At the same time, I would like to show you the top of a node, which will show you that XHPL is taking almost 100% of the CPU here. Almost all of the CPU this program is taking. So that's a good indication, but I still don't see it reaching 100%. That may mean that the problem size is a bit small, than it should have been. So we'll try that. You'll also see load going high. Okay, as you can see, 18 tests are done. They all have passed and completed successfully. No tests have failed, and I see about 6.1, 6.2 gigaflops of the compute performance. Okay, fine. Let's edit this file and let's increase the problem size a bit. Let's increase one more 0, and let's run the program again. But this time what I'm going to do is I'm going to send the output to, let's say, performance.txt file, so I can do other tests. What happened? This did not work properly. So let's first test without the this thing. What's this? Oh, memory allocation failed. So this problem size is too high for it. So 6000 was almost okay. We can try executing, reducing the one and increasing. Let's try with 8000. Does it work? Let's see if it works or fails. This is kind of a bit of experimentation. The original values were far low. It was like 24 and 30, and so you would definitely not want that. So the formula I've shown you, you use that. I've done it here. I'll explain that to you. Square root of 0.1 into output of free minus b from one node into number of nodes you have. So I have two number of nodes, so that's why I've mentioned 2 here, and this is almost the figure. And I'll just see what this does. It's taking 50 seconds. Great, it's now giving me 6.7 gigahertz. Problem size is 8000. Can we stop this here, and can we increase the block size to 200? Let's see what happens. Let's see what happens now. Okay, the first result is already out. 6.7 gigaflops I've already achieved. That's good progress. But that is how you manage. You just keep tweaking the HPL.dat. Somebody said in my colleagues it's black magic to handle HPL.dat and tune it to get the most computing power out of your cluster. If you go on your node again, you will see it touching 90%, almost 96%. Maybe it needs a bit more. We can try increasing it a bit more. Try what? Let's increase this to 10,000. Will it handle that? I don't know. It's already taking 44 seconds on each test. Let's see. HPL.dat. Let's change that to 10,000, and that 10,000 is still a multiple of 200. Make sure of that. So let's try running that. Gentlemen, the first test is out, and I see 8.3 gigaflops. That's great. That's great. Okay. Size of the problem is 10,000 and block size is 200. And what is my CPU doing on node 2? It's touching 95%. Good. 96%. 99%. Good. Great. So this means that LINPACK is configured, is installed, and that's how you measure the performance of your cluster. The last thing I'm going to tell you is what is the actual performance and what should be the performance of your cluster. While I check the performance through, I'll just put it in performance.txt, the output, and I'll let it run because each test is taking 80 seconds. So 18 tests would definitely take something like, I'm very bad in maths, 18 into 80 seconds. Okay, 1440 divided by 60. It's going to take about half an hour. So I'll just let this test run. I'll take this value 8.3 gigahertz and I'll show you what the actual performance should be like. I have this formula here. I've calculated this for you already. This is the formula. You use this. I have one processor in each node, one core. I have 4 flops per clock cycle in each. This is the value of normal day, modern CPUs or processors into 2.2 gigahertz. How do I know it's 2.2 gigahertz? Let me check here. Quit that. cat/proc/CPU info. Okay, it is 2.2 gigahertz. So I will just calculate it here. It's already calculated, by the way. One processor into one core into 4 flops into 2.2 gigahertz is 8.8 gigaflops. This is what I should get out of single node, out of one node, whereas I'm getting about 8.3 from two nodes. But as I've mentioned earlier, this is a virtual cluster. This is a virtual cluster, means if I can edit this file, let me just write it down here. So this one node theoretically I should get about 8.8 gigaflops, and for two nodes I should get 8.8 gigaflops into 2. That makes how much? Sorry, I'm too bad. 8.8 into 2, 17.6. Okay, is equal to 17.6. Efficiency is calculated as this. Efficiency is equal to obtained performance over theoretical performance. Forgive my spelling, I'm just writing in a sort of hurry, into 100. So that makes efficiency of my cluster is equal to 8.3 divided by 17.6 into 100. This should be in brackets. You know that already, I think. Okay, so that makes how much? Let's do that. I hope it is supported by BC. Oh, what should be, how should it be done? Suppose static here. Okay, never mind. It's less than 50%, but since I don't know how to operate this, Allah, let me just take out where is that calculator? I don't know where is that in Windows. Yeah, here. Okay, so 8.3 divided by 17.6 is equal to 47 multiplied by 100 is equal to 47.15. so this is going to be 47.15 is my, let me write it here, is equal to 47.15% efficiency. Oh, this is the efficiency of my cluster right now. I'm not ashamed of it because it's a virtual cluster. It will give me 50% of the efficiency. Why 50%? Because I'm running this software, this program on two nodes. If I do it on three nodes, three virtual nodes, I will divide it by it. I should get 1/3 of the efficiency, not half, and so on. If it would be a real cluster, you would get twice the efficiency. So assuming, just simply assuming that you got a real cluster and you got this efficiency, this 8.3 on one node, so what you will get on two nodes is 17.6. So in that case my efficiency would be twice of 8.3 is 16.6, right? Divided by 17.6 16.6, the theoretical, into 100. That makes up how much? That makes up, let's see, that makes up how much? Calculator, where is that? Okay, so 16.6 divided by 17.6 is equal to this, to multiply by 100. This is too damn good. I should use the word too damn good. 94. This is not achievable mostly. Even the big guys like HP, Dell, IBM, talk about software, Microsoft, none of them has been able to achieve more than 90%. It's 80%. Most of the time the efficiency is 80%. So if I get 16.6 on my 2-node cluster of this much with theoretical compute power, this much, sorry, then I should get this one. Oh great, simply great, I love it. This is not possible, so I'm expecting to get something like this. In fact, if I may show you, I have something here interesting. I think I have something interesting to show you. I just ran this on a real cluster. I'll just find the file and I'll let you know. Let's close this stupid thing. Okay, I have this. I ran this on this kind of processor, and this was the specifications. Just read here a bit. This is just to impress you, I know. It's a lot of things here, so I'll just go down. What kind of output should I search for? Okay, WR0. Let's search for WR0. So close that. Okay, I'm getting what? 1.4 into 10 to the power 2. That makes what? Let's see. That makes 147 gigaflops, and sorry, it's not readable from here. That makes, and theoretical peak performance of this cluster was 188. I calculated it up somewhere up, but just believe me on this one, into 100, and that gives you how much? 78% efficiency. Not bad, close to 80%. Good. So, and here is the actual tests. You can see I'm not lying. Okay, it's here. But the machine was, if I'll show you again, they were dual core, dual processor, 3 gigahertz quad core processors, 8 GB RAM each, 64-bit hardware, InfiniBand. Although I tested this setup on Gigabit Ethernet, not InfiniBand, I yet have to calculate that on InfiniBand, and I hope to have better. Measurements, better benchmark. Let's search for HPL.dat. I have it here somewhere. I think I'll show you what the values were in my HPL.dat file. I had this 46,000 as my size. It should have been a multiple of 100, I know. It was a 4-node cluster, basically 3-node cluster. This was a 3-node cluster, means 4 nodes were there. I was using 1 node as management node, and this does sound stupid. And my colleague, a senior colleague, told me later on that, Kamran, you should have it in a binary form. A number should be binary here, resultant number. This 3 into 1 is not binary. Either you use 2 here, or 2 into 2 4, or something like that. So this is how it was done, and I got about 146 gigaflops. So gentlemen, this was where is that? It's done or not? Okay, still going on. still going on. I hope to see. Let's have a quick check on this one, duplicate session, and I'll just show you if I'll be able to root red hat. Let's grep wr from the file slash cluster mpi user HPL bin this performance.txt file. Okay, so far the tests which were running, 1 2 3 4 5 6 7 8 tests have run so far. They took about 80 to 95 seconds and I got highest output as 8.25 gigaflops and still running. Okay, hopefully it will be done by some time or half an hour. I'll just close this video now, stop it now. It was great making these videos. Thank you for watching them. I know I made some stupidities, some stupid mistakes, but anyway, the main objective was to guide you, to show you how it can be done on a virtualized environment, how you can have a supercomputer on your own desk wherever your desk is. And good luck to you with your supercomputing, with your parallel computing, parallel programming. Happy supercomputing to all of you. Thank you very much.